Okay, thanks. It's interesting to see so many faces that I know kind of packed so closely, most of them friends. So anyway, let's not get into that. I only have so much time. Okay, so what I'm going to be talking about is obfuscating Turing machines. This is based on joint work with Venkata Coppola and Alison Bishop-Luco. Okay, so as listening to the previous talks, we are hopefully in this age of obfuscation where we can do something pretty amazing. We can take one existing program, run it through some compiler that we're going to call an obfuscator, and out we get is another program that is functionally equivalent to the first one. That is, it does the same thing, but we hope in some sense it makes it maximally unintelligible, hides the secrets of how we did the first one. Okay. So it's been a long time coming, but now we are at the point where we at least have the first, had in 2013, the first viable candidate for general purpose obfuscation from the GGH RSW paper. And here we were able to do it for obfuscating any polynomial size circuits. Okay, so circuits are great because they're a general model of computation, and we can, in some sense, do everything from it. But the main drawback with the model is that the description size of a circuit will scale with the maximum time it takes to compute a function. And in general, there might be some functions where the description is actually really small in the Turing machine model, but perhaps can run for much longer. Okay, so for that reason, what we like to be able to do is it would be even cooler in some sense to be able to do obfuscation for the Turing machine model where the description could be much less than the computation time or space. And I'll just mark this is an actual Turing machine I found online. It was kind of cool to look at in action. Okay, and the advantages for using obfuscation for Turing machines are that, first, the efficiency of encoding. We can also hopefully do obfuscation without bounds, like some program which can take an arbitrary length input. Also, for problems like delegation of computation or time-like puzzles, they naturally work much better when we're talking about Turing machine obfuscation than circuit. Okay, so towards this goal, there has been previous work to do it. And what they did was to build it on some type of definition known as differing inputs obfuscation. What differing inputs obfuscation essentially says is that no polynomial time attacker can distinguish between an obfuscation of program P0 and one of P1 unless it happens to somehow know a point at which these two programs differ. So this is inherently some type of extraction or knowledge problem, which says that if you're distinguishing between these two, I know that you know something about it. Okay, and there's, I won't go into the details, but there's a kind of a cluster of theorems around this showing that if we have differing inputs for circuits, plus we have snargs/snarks, we can translate this into differing inputs obfuscation for Turing machines. Okay. However, okay, so the main issue, though, is do we really believe in these knowledge assumptions? And one interesting result came out a year ago, which was essentially saying that there was a conjecture that there was a clash of functionalities for which we could not securely differing inputs obfuscate it. So if you actually believe this conjecture, which I personally happen to believe it, what this does is it sort of says that differing inputs is somewhat in the same boat as virtual black box obfuscation with the whole negative result of Barak et al. And I'll mention recently we've been working on some work with differing inputs obfuscation based on sub-exponential hardness assumptions. Sorry, here I didn't get the chance to. I just realized on the fly. We weren't sure if we're going to show that yet or not. Okay. Anyway. And there's also other things like public coin differing inputs obfuscation for which there's no known impossibility results. But there's not, like earlier was talked about some work of ours where we're trying to prove for indistinguishability obfuscation. There's not really, it's not clear like if there's even a path to proving things with differing inputs obfuscation. So for that reason, I personally think that indistinguishability obfuscation is in some sense the right definition to be working with, at least for some definition of right. And this is actually a slide I put up about 1.5 years ago at the Shafi and Silvio Fest, which is what we hope the future can be. Hopefully we can build indistinguishability obfuscation from some standard assumption, like learning with errors would be a nice example, of course. And on the other side of it, we like to be able to build up most of cryptography from it. Okay? And we've actually been pretty successful in that bottom half of the picture. I just picked out a few random or arbitrary examples of this. There's actually many, many more work done by many people in this area. And I'll even assert that on the top half, we've actually have had some progress. The first approach was put forth by is something for witness encryption put forth by Gentry, Luco, and myself, and then the work Amit talked about with Gentry, Luco, Amit, and myself, where we can try to break it down to a simpler problem. And in some sense, this has worked. We have broken it down to a simpler problem. The main remaining issue, albeit a big one, is just more the mathematics of these multilinear maps. Do we believe in them? But at least we have a problem which we can go on and narrow down. And I'll also mention there's also a second approach that works like the first one up into the point that they do this hybrid overall inputs for a compact FE. But then at that point, it deviates later on. And I think someone else will be talking about this work later on. OK, and the last thing that I really want to emphasize, because I know there are some doubts with these attacks on multilinear maps, I don't see any fundamental reason why this can't happen. Like, there's no real good argument. I mean, I can see why it's hard. I can see why it can take a lot of research effort. I don't see why it shouldn't happen, whether it's 2, 3, 4, 5, or even more years. This definitely, there doesn't seem to be anything hiding in there. Given all the other stuff we can do, I think this should be doable. OK, so now we're coming towards, we want to be able to use I/O for, we have indistinguishability obfuscation for circuits, or at least we believe we do. And what we want to do is to get indistinguishability obfuscation for Turing machines. So the most natural thing is, OK, how can I take I/O for circuits and somehow bootstrap it or somehow be able to turn this into I/O for Turing machines? And so for this, I'm going to point out 2 recent works towards this, which I'll call that have taken the entire state programming approach. OK, and the main idea here, let me kind of draw things, is that we're essentially going to have this yellow highlighted thing here somehow be an obfuscated circuit, and it's going to essentially run the Turing machine step. A step where you write to the Turing machine, you decide what the next position is. Do you move left to right, and what is the output? So essentially, we're going to just have some type of iterated circuit, which we take in some state, throw it into this obfuscated program, get some state back out, and just keep on iterating it over and over again. And here, I know obfuscation takes many inputs, but here I'm just going to focus on one particular input. OK, so the way that these, and I'll cite these works in a second, the way that these proofs work essentially are that they do a proof by a hybrid. And what they do is they, at some hybrid step t, let's say t steps in the hybrid, and all this gray area, I'll just simulate or pretend to do computation in some type of way. So I won't really be doing the computation here, won't really be doing the computation here. And then when I get to state t, I'm going to actually program in what the state should be. I'm going to say, OK, now we're doing the computation for real. Let me kind of somehow indistinguishability, somehow shove in the state. And from there, we'll actually do the real computation. So the point here for the proof is that we want to be able to show that first we program in it here, then we move it to here, and then we move it to here. And finally, we move it to the very end, where all the computation is just pretend, and you can't actually tell which program was used, at least on that one input. OK? Now, there's actually 2 different works that put forth this approach, which I'll call the entire state programming. One way was to use Yao garbled circuits, where the obfuscated program doesn't really do this Turing machine computation directly. It more produces a garbled circuit on the outside at one step, and then at the next step, it produces another garbled circuit, and these things interact with each other. And there's a second way. Where the computation is actually done on the inside of here, and what we get at the end is some type of signed state. OK? So these are 2 different kind of somewhat sub-approaches to doing this, but they both have the same thing. And there's also a RAM candidate that they have in this one that I won't get into. But they have one important thing in common, which is they both have this thing where at some point in the hybrid, you just program in what the state might be. Whether it's through a signed state or through a Yao garbled circuit, there's going to be some sim. Then we program in the state, and then we actually start doing a computation for real. OK? And however, the problem with this, or one drawback of it is, in order to program this state in, I essentially need my original encoding to be as big as the entire Turing machine tape might actually get. So if it might get to be X number of cells, I need this programming. I need the circuit over here to be that big. OK, and you might ask, OK, so why the memory restriction? Well, it's essentially what I said. If we want to be able to hardwire this in here, if we want to be able to hardwire this into the circuit, I need to actually say what it's supposed to be. So these approaches just say, okay, it's in some sense a lot like a standard hybrid approach for proving Yale-Garbled circuit. Here's what you are at this point in time, and then the hybrid goes on from there. Okay, and you might ask, well, how big of an issue is it? Like that we have that the encoding time, that the time and encoding size grows with the maximum size of the state. And I think the answer is it just simply depends on the computation, right? If the maximum state stays very small and is close to the program description, it doesn't really matter. If it grows significantly beyond that, then it does. Okay? And I'll point out that this seems like a fundamental, a fundamental property, at least, of this proof structure where I'm going to program in things and move forward from this point. Okay, so the point of this talk is, what can we do differently? If we want to be able to do I/O for Turing machines and not have this, restriction on the maximum size of the state, how can we approach this problem differently? Okay, so let me kind of jump forward to the end of things to start. So we're going to try to turn things around a little bit. In some sense, what we eventually get is we'll do a simulation, but more start the simulation at the end of the computation and move the hybrid in the opposite direction. So when we finally get to our final thing, it'll be more something like this. It'll be the computation will go, then it will hit some point, and then it will pretend to do the computation until it gets to the very end where the final output is hardwired. And to move the hybrid along, what we're going to do is kind of erase starting from the back towards the front. But one thing you'll notice here is that at no point do I say, okay, let's just shove in the state or program in the state at one point in time. Okay, so let's see how this is done. Okay, to actually describe this, I'm going to aim for a smaller problem than obfuscation, something called indistinguishability. Something called message hiding encoding. And the idea here is to be able to have a Turing machine M, and I want to encode a message such that a Turing machine M and input X, and someone should be able to decode and learn what the message is if M of X is equal to 1. Yeah? Did you define indistinguishable obfuscation for Turing machines, or is it completely trivial to see how it should be defined? I'm not going to define it formally in this talk. Is the short answer. But we'll kind of. I'm going to define this one, and then we'll kind of build up towards it. Okay. Thanks. Good question. Okay. So the smaller target that I'm going to aim for right now, that we'll kind of zoom our focus in on, will be message hiding encoding, where we'll take as input the encoding algorithm will take as input a security parameter, a Turing machine M, a description M, an input X. Some time-bound capital T. Just think of T as 2 to the lambda for lack of anything better, and a message. It outputs an encoding, and then the decoding algorithm will take as input this encoding and either output the message if M of X is equal to 1, or output bot, like reject, if it's equal to 0. Okay? And the properties that we want, are first of all, if M of X is equal to 1, if it evaluates to 1, you should be able to get the message. And the second one is an efficiency property, mainly saying that this encoding time maybe it's better if I stay over here. That this encoding time should be polynomial in lambda, and the description of the description message, and it's essentially independent of the running time, or maybe polynomial in log of maximum running time. Okay, the decoding time, on the other hand, can be polynomial in lambda, and also the actual running time of things. Okay.
So here, the encoding itself can compute whether M of X equals 0 or 1.
So you could, except for you would violate the efficiency condition. So in particular, like the encoding, the time to decide if M of X is equal to 1 will be T star, right? And I want the encoding not to take T star time. That's in some sense the whole point. If you didn't mind about that, then yeah, you just figure it out yourself and make the encoding the message. Make sense? Okay. So, those are the two conditions.
So what's the relationship between T star and capital T? Because it doesn't make sense. If I'm running for less than capital T steps, I might not be able to tell you if M of X is 1.
So if you're running.
So let's say T star is less than capital T.
Mm-hmm.
Then if I run for T star steps, or polynomial in T star, but T is exponential. Then I might not be able to satisfy correctness.
So let's just assume we're only interested in computations that take at most 2 to the lambda time.
This tells the actual running time on that
Just keep
particular
running.
X.
Decoding just keeps running. the
Oh, I
machine.
see.
Yeah.
Oh, okay, got it. Sorry.
Oh, no problem. Okay, and also the security property we want is that if m of x is equal to 0, if it's not 1, that it should be computationally difficult to distinguish between an encoding of message 0 and an encoding of message 1. And this is only when m of x is equal to 0. We don't have that on the slide. And in addition to being sort of a warm-up for the type of work we're going to talk about today, this actually is already good enough for many problems like delegation of computation, witness encryption, and time lock puzzles. So we can actually already get some stuff out of this message hiding encoding. I should also mention that Ishai and Rui actually, this kind of weakened definition, this is a weakened definition of randomized encodings that was also before this considered by Yuval Ishai and Hotek Hui. Okay, so the question is, how can we actually execute this type of an idea? And if I look at it, there must be two requirements. One is, if I don't want the obfuscated program to be operating on the entire state at one time, I need it to be operating on a commitment to the memory. So the memory, let's think of the memory as something really, really, really big. And the obfuscation needs to be operating on something much smaller than it. So it needs to be able to operate on a small commitment to the memory. However, if you've messed around with I/O proofs, you can tell it's sort of a tricky business sometimes, in that the I/O definition only works between functionally equivalent programs. So a lot of times to get an I/O proof to go through, you need some type of at least statistical or some type of perfect binding. So what we have here is two requirements. One is it has to operate on a small commitment to the large memory, and the second one is that it must be perfectly binding to it. And if you look at these commitments, it actually, I guess James Van Der Beek here gets upset because these things are actually a contradiction to each other, right? You can't be perfectly committing to this with something, really small here. Okay, so how can we make, I guess, our Dawson's Creek guy happier? Well, the main idea here is that if we're doing a hybrid, we don't need it to be perfectly binding at every step of the hybrid to everywhere. In particular, we just need it at a certain hybrid. I'm going to be looking at this place in the Turing in the Turing tape, and I just need it to be binding to there at that time, and then later on I need it to be binding to somewhere else, and later on to somewhere else. So what we're going to do is we're going to have some type of primitive which allows us to be perfectly binding to certain places at certain times, and we can move around which memory, which one is binding as part of the proof as we progress. Okay, and I also point out that, I don't know how to pronounce this, Hubacek and Wicks also had some type of similar selective enforcement idea for a different problem of multi-party computation that I won't go into right now. Okay, so here's one of our main abstractions. I won't have time to get into all of them for at least this memory store for doing this. And we try to coin this term IO-friendly tool. So the idea here is that we're going to pick a position I that will actually be perfectly enforced. Okay? And if anyone's actually read the paper, what I'm going to show you now is not the actual algorithms in the paper. It's going to be some type of simplified version of them to fit in the talk. Okay, so we're going to have two setup algorithms. One is a setup which takes in the security parameter 1 to lambda, and here t will also default as the maximum size of the memory, and essentially initialize this really large memory where everything is, I guess, initially uninitialized in some type of empty state. And what it outputs is some public parameters, the storage, this is where everything's stored, and a small commitment, which I'll call an accumulator to the memory. However, there's also an alternative algorithm, which is called setup enforced, which takes in the same parameters and along with I star, which says we are going to be perfectly binding to whatever happens to I star. That's essentially the point of this here. Okay. So next there will also be, and the point we're going to get at is that it should be hard to distinguish whether I executed this setup or that setup. Next we're going to have like a prep algorithm which essentially reads from the storage and also gives a proof that the read was done correctly. And there will also be a write to the storage algorithm, and this will be done by this outside part before I pass it to the obfuscated code and running the Turing machine. And finally there will be an update accumulator which takes as input the public parameters, the short accumulator will take as input the message at position I it used to be and the message I that I want to write. And it will either reject if this proof pi wasn't good, or it will give a new updated value to the accumulator of the thing. So this is our memory store object. And essentially we want everything to be, at least these operations to be polynomial just in the security parameter and log of t for these operations here. Okay? And the security property, again, is that essentially I can't tell which index I star that I'm going to be perfectly binding to. Okay. So let me, unfortunately, there's just kind of too much in the construction for me to go through it all, but I'm going to try to give a very rough picture of what's happening here. So again, we have this outside storage, right? And we're going to, the decoding algorithm, what it's going to do is going to have the outside storage, which we'll consider of the store, the whole memory, have a positional accumulator, the time step t we're on, the Turing machine position, the Turing machine state, some iterator hash, never mind quite exactly what that is on the values b through e, and some type of signature. We call it a splittable signature, but don't worry about that. Some type of signature sigma on b through f. Okay? And at each step, what we're going to do is the decode algorithm will first read at position POS, POS, gets the proof pi and m, and it will just kind of pass all this, take all this junk, and pass it to the obfuscated program. The obfuscated code will then essentially perform a Turing machine step. It will first check the hash, the signature, the accumulated proof, reject if any of these things go bad, poorly, and then it will output the step and update the accumulator, update the hash, and sign all these output values. So it's going to be just, we collect a bunch of stuff, run it through the Turing machine step, and then get out new stuff. The important thing here is that this big storage to this large tape is actually not passed in. So point A is not passed in over here. OK, then the decode algorithm will update the storage value. OK, so let me try to give you some sense about how selective enforcement works for the proof. Remember that we have that there is an initial encoding, and there is a deterministic decode algorithm. So there is a correct sequence of steps. If you look at all these values, the accumulator position 0, the accumulator 0, accumulator time step 1, time step 2, time step 3, that actually should be output, should be done in an honest computation, and we can just write these up on the board here. Now, the point is I want to be able to do a hybrid to be able to anchor it to the final result so you can only learn the message if m of x is equal to 1. So at hybrid t, we should want to hardwire things such that at time step t, we only output a good signature. Let's just say signature for now. We only output a signature if the correct accumulator value star is put in here. OK? And I am simplifying things a lot from the paper. I'm kind of taking out a lot of the details. There's more things you need to worry about. So we're going to hardwire in things to only work if the good accumulator value is there. And we want to just move the hybrid along for where we're first hardwiring in at pretty much the initial state until we hardwire in at the final state. And at that point, we can not show the message if m of x is equal to 0. OK? So, so here's the main substeps of the proof. We don't have too much time. At hybrid t, we're going to only output a good signature if the input to this obfuscated program is ac star of t minus 1. So this is a condition on the input of the accumulator. What we can do then is we can think of an intermediate hybrid t, an intermediate hybrid where instead of hardwiring at the input to the accumulator, we hardwire at the output. So we're hardwiring on the opposite side of the circuit. And then we go back to hardwiring at the next step of t plus 1. We're hardwiring at the input before. So what I want to talk about is how we get from here to here. And this is where, sure.
In this argument, is it important that you take your hybrid in the opposite direction?
Oh, this won't. This will happen after we get not for message hiding encodings, is the short answer. Yeah. So we'll try to get to that at the end, if possible. OK. Yeah. So I am doing a hybrid in the forward direction. That's a good point. OK. So let me describe going from here to here. We're going to change from hardwiring at the input to hardwiring at the output. And here we get another contradiction in a sense in that an I/O proof for me to get this through requires that this input hardwiring is functionally equivalent to the output hardwiring. In general, it won't be because this accumulator could correspond, one accumulator value could correspond to many different memory values, right? So the idea is before I try to execute this I/O type step of a proof, I'm going to first make it binding at the exact right place that it needs to be. So initially in a normal setup for accumulator sub t star, there could be many different openings of it. But what I'm going to do is I'm going to enforce it at position star for where there's only one particular opening that works. And at this point, the input hardwirings and the output hardwirings will actually be the same program in a sense. So this is where selective enforcement comes in that I'm going to selectively enforce exactly at the position I need to. And it's going to allow me to move this hybrid from programming at the input to programming in at the output. OK? OK. And then for this other step of the proof that we talked about here, I won't really go into this. This doesn't have to do with selective enforcement. Pretty short. So this would be some type of signature. I'll just call it I/O gymnastics. One important thing was that it kind of got determined not to use complexity leveraging for this, which made the problem kind of a bigger pain. And there was some primitive called splittable signatures. Okay, and so let me skip through that. But here's actually Shai's question, I think. So what happened with the whole backward simulation deal? Okay, so in order to get to indistinguishability obfuscation, we need to go from message hiding encodings to randomized encodings, which actually hide the computation going on. So construction changes, we go to oblivious Turing machine. We're going to encrypt our symbols instead of just putting them out in the clear. And so the proof really is that we use these message hiding type techniques to first anchor what the output's going to be. And then we erase one symbol backwards. And then we undo all that work. And then we anchor in what it should be over here. Then we erase another symbol backwards. And then so on and so forth. So actually, if the computation takes, let's say, t star steps, the proof is actually t squared hybrids, kind of a nested. So we have to pretty much use all the stuff I told you just to like erase one Turing machine symbol, then do it all over again, and so on and so forth. Okay, but at no point do we program. Okay, so so since I have only just a little time left, the main technical summary is that the principle is we want to avoid this whole state programming. We want to just do computation, at no point just say, here's your entire Turing tape. Selective enforcement would be perfectly binding when needed. This idea does not actually need this reverse simulation, but then we do this reverse order simulation using these ideas to sort of anchor things and erase one symbol. And going from randomized encodings to I/O is pretty simple. Okay, so let me finally conclude with just pointing out one of these we'll see next, that one of the most exciting things for me was to see in a short period of time how many works built on this. Oh, did I misspell something? Oh, whoops. Okay, well, now you got extra attention because of this. Okay, so sorry about that. Okay, so actually in a relatively short amount of time, a few months, there's been a lot of works that have built on this. One interesting thing is, with one exception, all these kind of weren't able to use it as a complete black box, sort of needed to break into these techniques and, I guess, deal with a lot of pain. Is that more or less correct? And deal with these primitives. Okay, so thank you, and I'll take any questions. Okay.